next test is a short circuit impedance test. I don't know if you remember when we were in high school, for some of you in high school, for some of you in university, we learned that two most basic tests of a transformer, any type of transformer, are short circuit impedance and no load test. Of course, ratio is important and winding resistance is important, but these are, let's say, more complex tests which more or less tell us about the losses in the copper and losses in the core. Short circuit impedance test tells us about the losses in the core. In the copper, in the winding. So what we are trying to see with this is how much does the resistance of the copper contribute to the losses of our transformer. You know, transformer does transform, but it has some losses. It is not a perfect device because the current which is passing through the winding, through the copper winding, faces some resistance on the way, which is low, but it is measurable, and that resistance makes a certain part of current turn into heat. That's why our transformer heats up, one of the reasons. So we will do this test, and we can also use STCS Plus as our device, as an accessory, which would help us make the test quicker. Why do we do this? Why not STCS? Because STCS doesn't have this option. Only STCS Plus has this option. In short, before we read this, let me just tell you the idea of this test. The idea of this test is to raise the voltage, is to first short circuit the secondary side. And important thing to know, short circuiting the secondary side has to be pretty good. You have to have a pretty thick wires in order to do that. Not wires, actually you need to have like small cables. And then you raise the voltage on the primary side all the way until you measure the nominal current in the secondary side. And then you express yourself in percentage, because that way you know how much voltage, what is the percentage of the nominal voltage which you need to generate on the primary side in order to reach the nominal current on the short-circuited secondary side. These numbers move from, let's say, 3 to 4 all the way up to 8, 10, 11, or 12%. The higher the number, the higher are the losses, so it's better to have a lower number. But let us read what is written here. It is the percentage of the normal terminal voltage on side required to circulate a full load current under short circuit conditions on the other side. So on primary side, we generate voltage, secondary side is short circuited, and we need to understand how much voltage we need to generate here in order to get nominal current here. For short circuit impedance test, why short circuit impedance test? To determine the maximum value of fault current that will flow under fault conditions, which is important, to see if there are some winding movement caused by some faults, and to see if we have some winding deformation caused while transporting. How do we perform the test? Well, this is more a theoretical part, and then we will show you the practical part. So theoretically, the test is conducted on the high voltage side of the transformer, and that is true in most of the cases. On low voltage side, we have a short circuit, and since voltage applied is very low compared to the rated voltage, core losses are neglected. How do we perform the test? Watt meter reading provides watt loss for copper loss, so what we're losing in the copper. Result is compared with the nameplate value, and error limit allowed maximum is 3% from the nameplate value. You will see that this 3% often follows us around, not only for winding resistance and short circuit impedance test. So this is an important number to mention here. So one example here, if we have 2 MVA transformer, which is 10 kV to 0.4, and we have Z percentages at 6%. So full load secondary, we can calculate like this, and we get 2,752.5 amps. Voltage required at primary for full load, because it's only 6% of primary voltage, it is 600 volts. So effectively, if we generate 600 volts on the primary and short circuit the secondary, we will get this current. Short circuit fault current can be calculated from this, and it is a big 45 kiloamps. If the fault if there is a fault at the secondary side of the transformer, then maximum fault current will be the calculated 45.8 kiloamps. Now, the parameters which we need to consider are, of course, full load copper loss, resistance viewed from the primary side, also impedance viewed from the primary side, and reactance viewed from the primary side, applied voltage, and rated current in the primary side. It is very important to remember that when executing this test, we should have, as we said, a very low resistance short circuit on the secondary side. If we take a small wire with not a big cross section, you will not get correct results. Whenever you're doing this test and you are getting the result which is, well, close but not correct, it is more than 3% difference, try putting a thicker cables, a thicker wires on the secondary side. So that's the suggestion. When we are actually doing a test, there are two ways how to do a test. You can either use, when you're testing, of course, a three-phase transformer, you can test three-phase equivalent method or per phase method. The number which you see on your nameplate is obtained by using a three-phase equivalent method. So, and also three-phase equivalent method needs to be used when you have a transformer which has a delta side. Only if you have a YY transformer, 2 stars, then you can use a per phase method, otherwise not. So when testing on a three-phase transformer, three-phase equivalent method, we actually need to do 3 measurements for phase A, B, and C. We see that the secondary side is short-circuited. And again, we will, in this case, generate not current like when we were doing winding resistance, but voltage. We will measure the current. So of course we are generating voltage, but then the current is passing. We are measuring that current and sending it to our transformer, and then coming back to close the circuit, and we are measuring also the voltage drop, as we can see here. We do it 3 times, and then the device automatically calculates the result using this formula here. If, on the other side, we have a per phase method, then we will do this per phase. So phase A, you see the difference is that when you're doing 3-phase equivalent, you're doing, let's say, BC, CA, AB, while when you're doing a per phase method, you're doing phase A, neutral, phase B, neutral, phase C, neutral. So that's the difference. You see, here you're connecting between phases for a 3-phase equivalent, and for per phase method, you are connecting phase and neutral. I strongly suggest mostly using 3-phase equivalent method because you are also often with a transformer that has a delta side. If your transformer has a delta side, you cannot use per phase method. When you execute a test, you will get a result, something like this. So for example, this is a situation where we measured 17.11, nominal value was 16, the deviation was 4%, which means that this particular transformer has some issues because this number is bigger than 3. So this is the thing you will get, the result you will get, and the easy way how to interpret that. So this is another example. When you will be doing the test in our application, you just need to say what is your maximum voltage and what is your maximum current. You perform a test on all 3 phases. You choose, this is the case where you can choose per phase, and then you choose which phase are you measuring, or 3-phase equivalent, and you choose which pair of resistances are you measuring. Now, frequency response to stray losses is the next test, but actually it is the same test. The difference, frequency response to stray losses, is short circuit impedance test, but done on different frequencies. And when you do it on different frequencies, of course, you get a curve. You get a curve like this, and because you get a curve like this, you want to compare the curve for all 3 phases. So keep in mind also that when you're doing this test, we short circuit the secondary side and we generate on the primary side, which is not the truth for the whole world. In some countries, they do it vice versa. They generate on the secondary side and they short circuit the primary side. With our equipment, you can do it both ways. So it is universal. And when you do this test, you compare actually phases. In this case, we can see that phases C and A are overlapping, while phase B is not overlapping with phases A and C. This indicates that we probably had some geometrical movement inside the transformer during a fault which happened recently, and that we need to look into phase B a little bit better. So this is how you would evaluate the result of this particular test. Let me just conclude. Frequency response to stray losses will provide us more information than short circuit impedance. Also, skin effect can be identified with FRSL test, and it is normally not identified during other routine tests. So skin effect is also an important thing to be taken into consideration when doing this test. You actually do this test to measure that. Next test would be no load current. No load current is a test which is often performed in factories. In that case, it is performed three-phase. So we have a three-phase, they have a three-phase generator, and what they do is they generate on the primary side with the secondary side open. We mentioned this test when we were explaining the turn ratio test, because in the turn ratio you generate on the primary side, and on the secondary side you measure voltage. But the simple fact that you are measuring voltage means like the secondary side is actually open, because the voltmeter has an infinite resistance. So we mentioned that the current which we see is actually the no load current. So how is the no load test done? The no load test is done by opening the secondary side and generating on the primary side. Once again, it is not the same in whole of the world. Later we'll see where do we have it differently. You can do this test with STS only, or you can also use STCS Plus or TD5000. You cannot use both of them, but why would you use STCS Plus? Because you would be able to connect only once and perform all the tests we've discussed up until now. That's the main reason. And the TD5000 you would use because maybe you want to generate voltage higher than 2 kilovolts, because with STS, 2 kilovolts is the maximum voltage you can generate. What can we understand by executing no load test? We can understand if we have abnormal core grounds, if we have some winding faults like short circuit or open circuit, which is, let's say, similar to no load test. So from this we see how no load test and turn ratio test are connected. We can see if we have some OLTC problems, and we can see if we have some manufacturing defects. So if everything is okay, we will have a certain current connected on the primary side, which will generate an electromagnetic field, a flux which will be conducted by the core, and then that flux will induce a voltage on the secondary side, as we see here. So let's see also how the test is executed. What we mentioned before is that we will generate a voltage on the primary side and the secondary side will be open. As we mentioned, the flux will run through the core and it will induce voltage V2. So the current, which will be actually running from the source, is the excitation current. We can put it like this. This excitation current is the current which magnetizes the core. If the core is not magnetized, then the transformer cannot work. So this is also the loss, but this is actually presenting the losses in the core. The same way that the short circuit impedance test was showing us the losses in the copper, this is showing us the losses in the core, and these losses are usually due to eddy currents which happen in the core. We know that the core is made from a laminated material, from a laminated metallic material, which are put together simply for the reason of having lower eddy currents. So if you have eddy currents big eddy currents in your core, you will see that losses while executing the no load current test. So what is the significance? Let's imagine that now we place a load on the secondary winding. Of course, there will be a current running through that load, which is a normal behavior. But that load, with the current which is running through the load, will cause a flux which will be actually opposing our original magnetic flux. So considering the voltage P2 is a constant, the voltage generator will have to provide more current to maintain the core magnetized equally to the opposing flux. So as the current starts to run here, and as it creates the opposing flux, we need to generate more from here in order to counteract that opposing flux. So one can say that excitation current is magnetizing current plus the current which is running through the secondary side. Now, if we get now a situation, for example, where few windings on the secondary side are short-circuited. You see this yellow part here means that for some reason the insulation on the windings broke, and we have now a situation where we have short circuit. Any short circuit on the secondary side will actually act as a load across a fault winding, and that load, as we mentioned before, will generate the current, and then we will have to oppose that current because that current will be creating a flux. So the excitation current will increase due to the opposing flux created by fault flux. Any short at secondary will result in an increase of excitation current. Long story short, we don't want to see a higher exciting current than previously. In this case, it would be very useful if you have previous results, but keep in mind that these results were made at certain voltage and with 3 phases generated at the same time. In our case, we can generate only 1 phase, so you will not be able to directly compare these results, but what you will be able to do is to see the ratio between them, and we'll talk about that in few slides. So how do we perform the test? We need to test each phase. We need to test with the highest voltage possible, and that voltage must not exceed the rated voltage. And we should compare with the previous results if we have them, of course. We can perform the test with only STS by using the 2 kV output, or we can perform the test by using also the tan delta addition. And this is what the connection would look like when we would be performing the test. We would generate on the primary side, secondary side would be open, and we would see the current which runs through this. We would read that current for phases ABC or RYB. This is what would it look like if we used our TD5000 as an accessory, and we would get a number. So we can say that you can, of course, when we will be performing this test, we use a UST-A mode, but this is something which concerns more tan delta. And finally, when we would get the result, what we would expect is that we have 1 phase which has values lower than 2 other phases. Usually that's the middle phase because you have less loss of flux in the middle, let's say, because when we have 3 phases, phase B is in the middle, and the flux is lost on the corners more on phases A and C than on the phase B. And for that reason, we expect usually phase B to have lower values. So that's how the result would look like. Here, in this case, it is particular because A and C have lower values than phase B, which is fine, but usually what we would expect is for middle phase to have different results. Interesting fact, this particular test is usually done by generating from the primary side with secondary side open, as we mentioned. But in some countries, it is vice versa. It is generated from the secondary side with primary side open. I saw that practice in Russia, Vietnam, and in some cases in Canada. But I'm saying that this is not according to the standard. Maybe it is according to the local standard, and it's fine. You can do it from both sides using our test set. You can generate from the primary with the secondary open, or you can generate from the secondary with the primary open. And this is how you would do this test. Next test is sweep frequency response analysis. Now, SFRA, or sweep frequency response analysis, is a test which you can do with just this device, with SFRA. You don't actually need STS 5000. But since they're all describing the health status of our power transformer, we put them all together as one family. What is SFRA? Well, SFRA per se is actually one of the reliable and sensitive methods to evaluate the mechanical and also electrical deformation of the transformer. So it is one of few tests which can tell you if after a big fault which happened, let's say close by, you have something moved inside of your transformer. And if that happened, the only way how to see that, the best way how to see that, will be actually running the SFRA test. The test is performed to obtain a transfer function. This is important, to obtain the transfer function of the transformer over a wide range of frequency. Actually, this is a pretty simple test. First of all, the device which is used to test is small. It is not a power device. You don't need to generate high current or high voltages. You will generate small current, low voltage on one side, inbreed on the other side. The only thing is, you can see from the name, sweep. Sweep here means that it will be done on different frequencies. And as you are generating this voltage on different frequencies and measuring on the secondary side, you will get a graph, which is a transfer function. But why? What is the theory behind this? Why do we do this test? So first of all, we know that in a transformer, we have a resistive elements, which is the resistance of the winding. We have capacitive elements, which are parasitic capacitance between the windings and the tank. And of course, we have inductance, with which we describe the windings on primary and secondary side. So, which means that all these three elements have different response for AC signal, and the response of each is related to the internal geometry of transformer. So, what we see here is that for resistance, let's say resistance, you can see here, this green line, resistance is always the same regardless of the frequency. We know that resistance doesn't depend on frequency, but inductance and capacitance, or to be more exact, the reactance caused by inductance and capacitance does change. So as the frequency increases, our capacitance, let's say the resistance is with increase of frequency, we are decreasing the reactance of capacitance, of parasitic capacitance, and with the increase of frequency, when we talk about inductance, the impedance increases. So we do have some, let's say, symmetrical features here. When we put together all three elements, then we get something like this. We get a curve which has a maximum or a minimum, or maximum and a minimum, which is important. And we can understand at which frequency that impedance is the highest. And this tells us something about the network which we have. And since we know that our network, that our transformer is a type of a network of R, L, and C, what we want to do is to get a transfer function. And that transfer function, and on that transfer function, we will pay special attention to the minimums and maximums. So what do we have? We have our transformer, which we model with some resistance, some capacitance, to be more exact, some resistance, some inductance, and some capacitance. We will have an input voltage, and we will measure the output voltage. But we will be going from, let's say, 5 Hertz to 45 megahertz. With SFRA 5000, you can go from 5 Hertz to 45 megahertz. In doing so, we will be using the logarithmic decibel scale to plot the result. So let's see what could it look like for a more simple system. If we have an R, L, and C, as we do have here, we can find what is the frequency response of that. So, which means that we will go from DC voltage to 10 volts, to 10 Hertz, to a much higher frequency. And this is how the impedance, or how the response of this network would be seen. The inductor has the dominant element in the lower frequencies, resistor here, and capacitor here. So transformer is a combination of resistors, capacitors, and inductors. As we said, resistance is the resistance of this is the core, this is the winding, and this is the wall of the tank. We know that there is a parasitic capacitance between this and this, and we know that there is a parasitic capacitance between this and this, and also this and this. So we need to take this into consideration. We didn't put it there, but let's use it to understand what is our transformer healthy, let's say. So we also have inductance. So all these three elements basically make up for a transfer function of this scheme. This is what we would call, this is what we would say a equivalent scheme of the transformer. Some capacitance of the primary side, capacitance of the secondary side, resistance of the winding of the primary side, and inductance of the winding of the primary side. Then we have some capacitance between primary and secondary side, and then we have also the secondary side. So if I generate 10 volts here, what will I measure here? Let's see. This is what we would use. This is how the connection is made. We would generate, let's say, on the primary side and measure, because with this device we have a very, very high accuracy. So at the same time, we are generating with one output and measuring with one input. And then we are also measuring from the secondary side. We also provide you with grounding braids to be sure that there are no noises given off by the substation, which would mess up with our results. And then when we do that, we get a result like this. Now, this curve here doesn't necessarily mean anything to us if we don't have a previous result. It is absolutely necessary for these types of tests to have a previous reference curve, because the previous reference curve is what we use to compare the present curve, and if they overlap, we have no issues. If they don't overlap, then we have issues. What we also do is we focus on certain points and we focus on certain regions. Let's say here we can divide this into 3 parts, and you can say that this first part talks about the core, then this one talks about the windings, and then this one talks about bushings. So if we overlap 2 curves and everything is okay here and everything is okay here, but here we have issues, we know we have issues with bushings. And if everything is okay in this third part and the second part, but the first part is different, then we know we have issues with the core. So these are the ways how you can basically evaluate the results. So, just to tell you, you don't have to do it. Actually, you don't do it. It is automatically done by the software which we provide you when you purchase a test set. We don't just plot magnetic gain versus frequency, we also plot phase versus frequency, how the phase shift changes with the change of frequency. And then we have 2 graphs at the same time, which tells us, which actually give us something which we call like a fingerprint of a transformer. So this is what you have right now, and then if something happens, you will repeat this test and you will overlap these 2 results. If the curves are the same, you're fine. If not, you try to understand where do you have issues. And then we said we're going to talk about important points. The important points are points of inflection, the minimums and the maximums. You see here minimums, you see here the points where something starts to change. The inflection points are the points which are the most important. You might have 2 values which are not the same here, but if they don't overlap when it comes to minimums and maximums, that's a bigger issue. So inflection points need to definitely overlap over each other. And that we can see here, because this gives us a fingerprint of the transformer, and the fingerprint should always be the same. When do we do an SFRA test? We do it always, the manufacturer does it. The manufacturer actually does it to ensure himself that through the process of moving the transformer, while it is being transported from point A to point B, nothing hits the transformer, because if it does, the producer will do an SFRA test in their factory, and when the transformer reaches its final destination. If, when the transformer reached the final destination, we do an SFRA and the points don't match, it means that something went wrong during the transport. Let's not forget, once again, this is being done mostly to understand if we have some geometrical movements inside of the transformer. So we do it at the manufacturer place, pre-commissioning check. This means when the transformer came to the substation. When a weakness of the winding mechanical pressure system is known, so old and suspected unit, when a short circuit fault has occurred. Why? Because if we have had a huge current running through the transformer, the electromagnetic force of a big current can sometimes physically move a winding, or it can move core inside and thus make the transformer geometrically different than it was before. Also, something that can shake a transformer is an earthquake. Let's hope it doesn't happen. So also, what can an SFRA detect? It can detect if we have a core deformation, if we have also earth core removed, if we have an additional earth core, if the core is magnetized. So we mentioned before that when we do a winding resistance test, the core is magnetized and we need to demagnetize it in order to be able to use the transformer again or to test for SFRA. We can see if we have a collapsed winding or if we have a radial deformation. Some other defects are also, we can see if we have a raised and lower winding. So you can see collapse deformation, radial deformation, raised and lower winding. These are all geometrical problems. So physically something changed in the outlook of the inside of the transformer. We can see if we have some unclamped winding, if there are some shorted turns, also an open circuit, broken conductor strand, or unclamped core. All these things can be seen by SFRA. Now, what are the key points of SFRA is how we connect. Also, mentioned before, we need to demagnetize, or let me just say before we do SFRA, or let's not do SFRA after the DC test. And the database range should be at least 120 according to the IEEE standards. So IEEE standards actually asks for 100 decibels, but to be sure, it is good to have a little bit of margin and to go up to 120. The plots to the SFRA or the tests which need to be done is high voltage side. If we have a star point, if we have a star connection on the primary side, we do it neutral to phase or phase to phase. Neutral to phase is for a star and phase to phase is for a delta. Open circuit plot, short circuit plot with load side shorted, and on the low voltage, the same like for the high voltage again. And if we have a tertiary, again, neutral to star on phase to phase if we have a delta. So the key features, actually the voltage which we are generating is from 1 to 10 volts peak to peak. So it's very, very low voltage. Dynamic range is 120 decibels, like requested by IEEE, and the frequency range is from 5 Hz to 45 megahertz, which is more than enough. Accuracy is extremely high. We're talking about 0.02% plus or minus 0.05% per megahertz. So the accuracy is 0.07 worst case scenario. Phase is 1 degree maximum error, and the fact that this device has a built-in display is very useful because more than once it happened that the users would connect, start testing, execute the test for whole primary and maybe sometimes whole primary and secondary side, and then they would realize that something went wrong. And they wouldn't be able to see that during the execution of the test because the device wouldn't have a screen. So the screen is always a good option to have if we want to be sure that the connection was done properly. Also, some key features are the fact that we have a dedicated PC software where you take both values, both readings, and it automatically tells you if you have issues or not. We also provide you with grounding technique using braids, and the device has a battery operated with a battery that can last up to 5 years. Number of points is up to 2,000. So for 2,000 points, you can create a transfer function. And the length of cable is also important because 18 meters is more than enough to test your power transformer. So this is the set which we provide you with. You can see 18 meters of cable here, the device is here, the braids are here, and you also get this nice box including the clamps which are inside. Our last focus, and our last focus will be a tan delta test, and after that demagnetizing. I know that it's 11:30, please bear with us 10 more minutes and then you will be free to go. So when we talk about tan delta, when we do a tan delta test, we absolutely need TD5000. Without that, we won't be able to do that test. So that's number one. Tan delta is an AC test used to determine the state of insulation. It is performed at a high voltage, usually 10 kilovolts, but you can go up to 12 with our test set. And of course, it is a skilled operation, is fundamental for consistent measurement. What do we measure? We measure actually the capacitance of the insulator. So the capacitance of the insulator we mentioned before when we were talking about SFRA, there is some parasitic capacitance over there between the primary and the secondary side, between the primary and the ground, between the secondary and the ground. And by measuring it through time, we understand if something changes. Also, we measure the R component, let me put it like this, and we will explain why. So in an ideal case, since we model the insulation with the capacitor, we have only capacitive current. As you can see, we have a capacitor here. But we know that originally we have a capacitor and the resistor. We know that in a starting state, we have a fantastic situation when it comes to our power transformer, where the voltage is lagging 90 degrees or very close to 90 degrees. But in a real situation or after some time, because the deterioration of the insulating properties of our insulation, it is not anymore 90 degrees, but now it's less than 90 degrees. Let's say it's 89. 1 degree makes a lot of difference. This happens because in course of time, the insulation degrades. It gets older and the impurities inhabit the system as isolation starts to degrade. Effectively, what happens is that water gets inside, gases get developed. Also, there is sludge, which all contributes to the conduction, or let's say it decreases the insulation. And that's why we want to measure this angle. This angle here is the delta angle. It should be 0. But if it's more than, let's say, 0.6 degrees, for transformer, you have a problem. So tan delta is actually the resistive component of current divided with the capacitive component. And here it is written, it is drawn in a way which is very unproportional to the realistic situation. Normally, this current here, the resistive current will be very short, like up to here, maybe not more than that. But then this angle would be very small. As I said, this angle has to be very small. So since we talk about the ratio between the in-phase current and the capacitive current, this is the definition of tan delta. Another name for tan delta is dissipation factor, and we also have another name, power factor. It is slightly different than tan delta, but for transformers and even up to 5 degrees. So if the delta is up to 5 degrees, the value of tan delta and power factors are the same. Just to show you one thing, if the angle is 90 degrees, tan delta is 0. If the angle is 89.8 degrees, and we are talking about this angle here, if it's 89.8, which is very, very close to 90, we already have tan delta of 0.2. If it's 89.5, then we already have a tan delta of 0.5, which is for some transformers the threshold. So it should be a very small angle, and usually it is, because we mentioned at our last webinar that 0.5 degrees, 0.5% is the maximum value for tan delta for a new transformer. In some rare cases, producers go up to a slightly higher values if we talk about medium voltage transformers, but the higher the voltage on the transformer, the lesser tan delta can be. Now, your service age transformers can have tan delta between 0.5 and 1%, But if the tan delta or dissipation factor is more than 1%, it is a call for an alarm, and then maybe you can do a tan delta sweep, or you can maybe do some other tests to understand, do you really have a problem with insulation or not. That can be a partial discharge test, or you can even put a monitoring system on your transformer. So this is what a sweep would be if you do a measurement of tan delta at different voltages or even at different frequencies. In this case, it's different voltages. This closes our tan delta discussion and brings us to the absolutely last topic, demagnetizer. Demagnetizing is not a test. Demagnetization is needed after winding resistance test. It is different from de-energization. De-energization is when we take all the energy from the transformer, which means that after de-energization, if I touch two phases of a transformer with my fingers, I will not get a shock. But at the same time, the transformer can still be magnetized, which means in a BH plane, this would be your BH plane, you would not be in the point 0, 0. You would be somewhere else, which means your transformer is not properly demagnetized. During demagnetization, STS will use STDE. It is this switch box here. And how will it function? It will generate DC currents in alternate directions in order to demagnetize the core of the trafo. Effectively, what will it do? It will go 6 amps in one direction, then 5 amps in another direction, and then 4 amps in this direction, and then 3 amps in left direction, and then 2 amps in right direction. So it will be decreasing the DC current and alternating the direction. What is it doing? But in doing so, it is creating all the time smaller and smaller area of hysteresis, so that in the end you reach the point 0, 0. So in a BH plane, what actually happens is that the area of the hysteresis curve continuously decreases until we get to the point 0, 0. If not performed after winding resistance test, we can have tripping for second or fifth harmonic, and it should be done on all sides and all phases of power transformer. What do I mean by that? I mean that you choose your side of the transformer, you choose your phase, you put tick here, you press start, and then you demagnetize. What you would see in this graph, you would see current going up and then down, but a little bit less, and then up, but a little bit less, and then down, less, up, less, until you reach the certain point. So one needs to choose which phases and which sides of the PT to demagnetize. Next step is choosing the current with which we will do that, let's say with 5 or 6 amps. We press the start, and process is stopped automatically when the core is demagnetized. So this is actually the last slide of today's presentation. I want to thank you for your attention and to say that you can contact us on at this email. You can concretely contact me, andrei.sepcic@altanova-group.com. But you can also visit our website, our beautiful website, www.altanovagroup.com, and find our regional offices or our local distributors. Thank you once again for your attention, and enjoy the rest of the day. Bye-bye.